Welcome to Level 1, York, Pennsylvania, the first lecture on Earth chemistry. To begin, let's talk about matter. Matter is anything that takes up space and has mass. So, for example, you are matter. Books are considered matter. Air is also considered matter. It's hard to think of air as having mass and taking up space, but it does. If you look closely through a microscope, you would see little atoms. Can you think of anything that is not matter? So in other words, can you think of anything that does not have mass and does not take up space? One example would be heat. Heat does not have mass and does not take up space. Can you think of another example? Gravity would be another example. It does not have mass and it does not take up space. Atoms are building blocks of matter. Atoms can combine to form compounds, and they can change their physical and chemical properties. An element is matter that only contains one type of atom. For example, copper wire only has copper elements or copper atoms. Sulfur rock only contains sulfur atoms. And you'll see later, or rather you will smell later, that sulfur can get quite stinky. If any of you have ever been to Yellowstone National Park, you would know. The Earth's crust is made up of 8 main elements. There are 92 common elements, but the crust is only made up of mostly just 8 of those. And if you look at them, 46.6% of the crust is made up of oxygen. Yeah, the stuff you breathe. Although this oxygen is not going to be in gas form. It's mostly going to be attached to something else. What might that something else be? It could be a lot of things, but the most common thing is silicon, which is used for computer chips. So if you look at oxygen and silicon, they add up to be about 74%. So the Earth's crust is made up of mostly oxygen and silicon. Next up on our list with 8% is aluminum. Yep, that's right, the stuff you drink soda out of. With 5% we have iron, such as iron gates. Iron can also be found in your blood. Calcium is found in a lot of dairy products such as milk, and calcium is used to build your bones. Sodium is found often in the kitchen with baking soda. It's also part of salt. Potassium can be found in bananas. Potassium will also help you out if you're having muscle cramps. And last, magnesium is used in road flares and fireworks. That leaves 1.5%. So of all the other elements, they're all going to add up to only be 1.5%. If atoms are so small, how do we study them? Well, we can build 3-dimensional models, or we can build 2-dimensional models. We can also look at them through really big microscopes called electron microscopes. Okay, this should be a review. Parts of an atom. Protons have a positive charge, so in my diagram there, I gave them a happy face because they're nice and happy and positive. They have a mass of 1 AMU. AMU stands for atomic mass unit. Protons, neutrons, electrons are so tiny, we have to come up with our own way to measure them. So we call them atomic mass units. So they have a mass of 1. They are located in the nucleus, or the center of the atom. Neutrons have no charge. They're neutral, so I gave them a face that has a neutral or a flat-lined mouth. They have a mass of 1 AMU as well. They're also located in the nucleus. The electrons have a negative charge, so I give them an angry face. They technically have a mass of 0.0005 atomic mass units. If we round that, it would be 0. So for our simple addition calculations, we're going to assume that they have a mass of 0 atomic mass units. They're located in the electron cloud, which is surrounding the nucleus. Okay, grab a piece of paper and a pencil and try to draw an atom with 2 protons, 2 neutrons, and 2 electrons. You may pause this video if you need to. Okay, flying around the outside of our atom, we are going to have our negatively charged electrons. In the inside, we will have 2 positively charged protons and 2 neutrally charged neutrons. Elements are defined by how many protons they have. For example, hydrogen only has 1 proton. If you add another proton, it's no longer hydrogen. It's now going to be helium because it has 2 protons. If you take away a proton, it changes it back to hydrogen. If you change the number of neutrons, it'll change the mass of the atom, but it won't change the actual atom. So if you take helium and you take away a neutron, it's still going to be helium. Same thing with electrons. If you have helium here has 2 electrons, if you take one away, it's still going to be helium. But if you change the protons, that's going to change the name. Okay, the atomic mass of a proton is just how much mass the entire atom has. So you have to add up anything that has mass. So all the protons and all the neutrons. The atomic number is how many protons an atom has. So this is usually a smaller numerical number than the atomic mass. On a periodic table, you'll see a symbol. Si here stands for silicon. And this is your symbol. The smaller numerical number, which is not always on the top, but the smaller numerical number, that is going to stand for, can you guess? The atomic number. And that is the number of protons. And so the last number down here is the atomic mass. And that is protons plus your neutrons. Changing states of matter. So states of matter would be your solid, liquid, or gas. And when you're changing your states of matter, you're not changing the chemical properties. So in other words, if you take water and you freeze it, it's still H2O, it's still water. If you melt that ice, it's still H2O, it's still water. So you're probably familiar with solid, liquids, gases, but there's a fourth state of matter, and that is plasma. So let's go back. Solids here are where atoms are in a fixed position, meaning they don't move around relative to each other. Liquids are strongly attached, but they're not fixed to each other. Gases move very freely. And a plasma example would be a lightning bolt because it has mostly ions and electrons. Okay, so a solid there, you see it's in a fixed position. Imagine if everybody sat in their seats, we would be in nice rows, and if we were to link arms, we'd be connected. That would be a solid. A liquid, imagine you're in a hallway filled with lots of students, and you're walking through the hallway. You guys are close, but you're not attached to each other. You're not walking arm in arm. You're moving about as you will. Gases are much more free, much more spread out. So imagine there are 5 students on a football field, all spread out. Plasma, again, those are your ions and electrons. I gave you a picture of an example of a plasma. If you ever put your hand on one of those, the blue lines will be attracted to your hands. Okay, so some definitions, some that you've probably heard before, some maybe not so much. If we go to a solid to a liquid, you're familiar with the term melting. We also use the term liquefaction because you're making a liquid. Liquid to a gas is evaporation. Gas to a solid, deposition. Going the other way, solid to a gas is sublimation. A gas to a liquid is condensation. And liquid to a solid is freezing or solidification, meaning making a solid. In order to change between these states of matter, all you need to do is either add heat or take heat away, and you'll change the states of matter.